If this squared wasn't here, arctan, we're done. But it is. So we have to rewrite this as square root x squared plus 1, that to the 4th power. If I say square root of x to the 4th, that's really x to the half, that's square root, to the 4th, and you multiply these, and that's x squared. So another way of writing x to the x squared, or something squared, is to write it as the square root of it to the 4th. Now, what's the trig sub I'm going to use here? X is a tan theta, so trig sub. Using x is equal to a tan theta. What's a for us here? 1, right? The square root of that. So it's just tan theta. So dx is secant squared theta, d theta. And the square root thing is secant theta. I'll save us the time, but that's what would happen if you go through and replace x. And is that okay to do that? Replace that with tangent theta, square tangent squared theta plus 1 is secant squared theta, square root of secant squared theta is secant theta. So you would get that. All right, I get to rewrite this in terms of theta. Integral 1 over. Yeah, this right here is secant, but then to the 4th, right? Secant to the 4th theta times dx. Don't forget, dx is secant squared theta, d theta. You get 2 of the factors of secant to cancel. Hey, where's my 1/2? Did y'all let me lose my... Oh, no, the 1/2 went away. That's right. Okay. That's right. All right, so when you have this left, you get 1 over secant squared is left, which is cosine squared. Yeah? Yep, so you've got cosine squared theta d theta. And when you have cosine to an even power, you're going to use the power reducing or the half angle identity. It becomes 1 plus cosine 2 theta d theta. And remember the 1/2 that comes out of that formula? Right? I'm rewriting cosine squared theta as 1/2 parentheses 1 plus cosine 2 theta. And that you can integrate term by term. 1/2 parenthesis antiderivative of 1 theta plus antiderivative of cosine 2 theta 1/2 sine 2 theta. But we know from last class and from the homework that when you have sine 2 theta, that's not going to be good. So you have to use the double angle formula for the sine 2 theta to get it back to sine theta cosine theta. So this becomes 1/2 theta plus 1/2 times 2 sine theta cosine theta plus c. It should feel like we're doing math now. This should feel like we're doing math, all right? We've come a long way from this, right? We've come a long way from this now.
I missed that.
You missed this, right? What I kind of learned when I was a Cal 2 student is that, like when I was looking at this problem, I was like, oh my gosh, like this is actually like unraveling into this big monster of a problem. And I was like, is it supposed to be that way? Yes, that's the answer. Like, yes, it is this involved. There is this much room for error in here, right? Remember, we're still in one integral of 2 integrals that we've done. So if it seems like a lot, it is a lot.
So do we combine them now?
Now, we need to figure out what theta is, sine theta, and cosine theta. So this is where you go to the reference triangle. This was based on our trig sub, which was x tan theta, is tan theta. From that, I can get theta by taking arctan on both sides. But then to create the triangle, I use that tangent theta is x, which is the same as x over 1, right? So how about x here, 1 here? And then the hypotenuse is square root of x squared plus 1. Substitute it all in, and we're there. All right, theta, arctan, x, right? Those two went away. Half and 2 are gone. Plus sine theta, opposite over hypotenuse. Cosine theta, adjacent over hypotenuse. We can put these two together, right? Multiply across, the root times the root goes away. 1/2 gets passed through everything. And we're there. At least for this integral, we're there. Plus, what is that? 1/2. How about I do it this way? So I put the x and the 1 together, I put these two together, the root went away, but then I had the 1/2 that had to distribute to both, so I put it down here as a 2.
And then you put it into the other.
Final answer. The integral of x plus 1 over x squared plus 1 squared dx is equal to negative 1 over 2 times x squared plus 1. Was it negative 1?
Yes, sir.
Okay. And then plus 1/2 arctangent of x, and then plus x over 2x squared plus 1 plus c. Yeah? I see some like terms here. This and this have the same denominator, don't they? So I could put those together, combine their numerators together. I just get x minus 1 over 2x squared plus 1 plus 1/2 arctangent x plus c.
If we don't clean up our test, you won't do that, right?
Clean up. Like if you wouldn't have done that on the test, I probably wouldn't care. I'd be proud of you for making it that far. Because that is a small journey, isn't it? Yeah, so the derivative of that should be that, right? I'm pretty sure it is. So I was going to come on here and I was going to do something. This kind of ties into, oh, my internet's turned off, hold on. The section after this section, and we won't even get into it, you won't be tested on or anything, but the section after this section, 6.4, talks about tables of integrals in computers in integration. Basically saying, hey, look, you know, your formula sheets, like there's books that are hundreds of pages long full of formulas, or the internet and technology will also allow you to do integration. And our favorite website for doing math is Wolfram Alpha, right? Mathway is better? Because Mathway explains the answers. Yes? So Wolfram Alpha is not the go-to anymore? No? What's better? Mathway? What does Mathway do? I need to keep up with the times. Come on, tell me. They'll show you step by step with Mathway? Should I go to Mathway?
I don't know if it's free.
Oh, it's not free?
I don't know.
Oh. Okay, so integrate. What do I want to integrate? It was, forgot the problem. X minus 1? X plus 1 on the top, divided by, I need to get this right. It's, I'm going to use 2 parentheses, x squared plus 1, right? But that's squared.
I think our cast calculator does it too.
Oh yeah, If you have a TI-89 or TI-Nspire CAS, it'll do it. This was a little faster, I admit. That's it, right? What's that? Yeah, yeah.
They do it for you too.
Which one do you have? The
I have,
Nspire?
I have both.
Oh yeah, that's why I don't allow those on tests. The computer algebra system calculus, that's why it says it in the syllabus. Now, I have not told anyone that they can't use their calculators on the test, but the people who do, especially on the second test, I'm going to be just making sure that you are doing your work by hand. All right? So this begs the question, like, if the computer can do this, like, why are we doing it, right? So, like, why are we actually going through this rigorous step by step? And I think that's a valid argument. And I think just from my perspective, historically speaking, computers used to not be able to do this, right? You couldn't just go onto the web and get this. And I think it's taking time for textbooks to actually catch up. And I think we need to move more in this direction. But right now, I can't require everyone to have a TI-89 or whatever where you could just use your calculators to do it. If I could require everyone in here to have a $150 calculator, and this was a technology-based Cal 2 course, then we could just kind of like breeze through the techniques of integration, use our calculators and do a lot more application problems. But this is still a classic Calculus 2 class, which means we're doing a lot of this by hand. So I get you, I understand your point of view. I'm big on technology. I want to see it turn in this direction. But the other side of the coin is you still need to have people that understand what's going on, right? Like, is this computer program made by this company, Wolfram Alpha, is this just like some really smart person sitting there waiting for someone to type an answer, like questions, and they're just typing the answer? I mean, there's an algorithm. The computer is actually working through an algorithm. Who writes those algorithms? Mathematicians and computer scientists. How do they get these algorithms to work? They understand the underlying principles that you're learning right now. They're understanding how this is all working, and then they're able to do this. If we stop teaching the underlying principles, then at some point, we have no way of verifying whether or not this is a correct solution or not. When I was in graduate school, I took a course called numerical analysis. And there's this theory that mathematicians and computer scientists it's not an official theory, but it's this idea of what's called the black box. All right, so you have your problem that you spit into Wolfram Alpha, or if you're an engineer, into your engineering program, or if you're, depending on what field you're in, you usually every field has like the program you use for that field, right? CAD, computer-aided design, right? CAD, everyone trusts that software, right? And you get your problem in, and then you get your answer out. Well, what's happening in the program is the black box. And when I was in grad school, what we had to do as a project was we had to pick 3 commonly used computer programs. And then what we had to do is we had to get into the code, within the code of the program, and try and exploit weaknesses within the code. So that what we would do is we would come up with a problem that we would solve on paper theoretically by hand, and we would have a solution that we know is right. And then exploit the weaknesses within the program to get a false correct answer and show that that black box can't be trusted. Does that make sense? If you stop teaching the theory, then there's no way to check this, and everyone just trusts the answer.
They make you do something like that, like your higher up math class. They make you use like you learn how to use like Java and decoding. And they have a math class like that. They make you plug it in. They make you do it on hand paper, and they make you also do it on a computer to match.
To match the answer, yeah. So like all algorithms have weaknesses. And so like that Wolfram Alpha website, their algorithms are so complicated that even if you give it a problem where you try and exploit a weakness, their algorithms will actually like filter out the weak. Like if you type in a problem trying to exploit a weakness, it can identify whether or not the algorithm is going to be weak, and it'll kind of branch off to a different algorithm that will address that weakness. So that the algorithms are getting better and better and better. It's hard to stump these computers, but again, it comes to that theoretical thing, like what if nobody knows how to do the math anymore and we're just trusting these algorithms, and do we want to go there? I don't know. We need at least some people to still know not the algorithms, the theory, right? Okay. That felt good though that we got the right answer. And then the other argument is that, look, I mean, this is just a higher level of thinking, right? You have to organize a lot of ideas. You have to put a lot of things together, right? Problem solving. That's what we want from engineers, computer scientists. We want problems like that to not be too intimidating. All right, we have some time left, and I'm going to have enough time to get into one example here. The whole reason we did all of that was to lead us into this. How do we find the antiderivatives of rational functions? So let's just remember what a rational function is. It's a polynomial divided by a polynomial. Here are some examples of rational functions. When it comes to integrating these functions, there's kind of a set of steps that we can follow. And the first step is to look at the degree of numerator and denominator and compare them. So let's just go through these real quick and talk about the degree of the numerator and degree of denominator. What is the degree of the numerator here? Denominator? 1. Degree of the numerator? Denominator? So we're looking at the highest power of x, right? 4 and 3. 2 and 3. 2 and 2, right? Okay. Here's the general strategy for integrating rational functions. That's it right there. Okay? Got it? All right, so let's just go ahead and do it. There's a lot involved here. But the first step is to inspect the degree of the numerator and denominator, just like we just did. If the degree of the numerator is less than the degree of the denominator, then we're going to move on to step 2. If the degree of the numerator is bigger than or equal to the degree of the denominator, then we have to do long division first before we can begin. And then we move to step 2. Okay? So the example I'm about to put up here, well, let's do it. So all of this other stuff right here, all that, just ignore for now. Let's just try and do this first one. Do you all remember partial fractions from pre-cal? All right, we'll find out. And trust me, I'm going to help you along the way, okay? I'm not going to just be like, and obviously from pre-cal, I mean, I'm going to kind of lead us. But I would recommend that you go back and take a look at it. You've got Google, right? You've got YouTube. Look up partial fraction decomposition and, try and get the basic idea of it down. It can get pretty complicated, so. All right, we have a rational function. We want to integrate this. Now, we would have to go through our ideas, basic U sub, integration by parts, trig substitution, right? All right, all these different ideas. What, x1 what? Yeah, so if we look at this and say, hey, look, wait a minute, this is a rational function. I have a polynomial divided by a polynomial. Then according to the steps, I should check the degrees first. Degree of numerator is 3. Degree of denominator is 1. If that happens, degree on top's bigger or equal to the bottom, long division occurs first. Right? Yeah. Yes? Okay, so let's do long division. I know you all love long division. It's just something you do on your spare time. So this is the way it goes with long division. It's the good old division box. The numerator goes in the box, denominator goes outside the box, and you make sure they're in descending order. So I'm going to put the denominator on the outside. On the numerator, x cubed, I'm going to also put a 0x squared to account for that gap that we have between the x cubed and the x term. That's pretty standard when it comes to long division. Now look familiar? And then you play a little game. You say, all right, what do I multiply x by? Just the x, forget the negative 1. What do I multiply x by to get x cubed?